In the last class, we discussed about the different biasing schemes used for amplifiers, and we have studied about the significance of proper biasing scheme, so that a weak signal given as input can be faithfully amplified without any distortion occurring at any portion of the signal. So, now today we will be discussing about the amplifier which is used for such amplification of weak signal with different biasing schemes, and today we will be starting with discussing a BJT amplifier in the common emitter configuration. So, the common emitter BJT amplifier with fixed biasing scheme will be discussed first. So, the fixed biasing scheme, as we have studied earlier, is having a biasing resistance given here by this RB. This resistance is connected to base terminal and it shares the same VCC with the collector which is used for reverse biasing. We are taking for an example an NPN transistor which is common emitter configuration. So, here apart from these biasing resistances, there are capacitances which are used for coupling the signals. So, the C1 is the input coupling capacitor which is coupling the signal Vs, and the output which is obtained at the output terminals, this output is V naught, and this output is obtained by coupling the collector with a capacitor C2. And this Vs, which is the input signal, this is having a series resistance Rs, and we are getting the output voltage V naught across this load resistance RL. So, this amplifier has the source resistance Rs in series with the source Vs, and it has a load resistance RL, and we are getting the output voltage across this load resistance. And Rb is the resistance which is connected in the base for biasing, as well as Rc is the resistance at the collector. So, this scheme is a simple biasing scheme which is known as fixed bias scheme. So, now in order to know how this amplification is taking place by considering the AC equivalent circuit, we can proceed now to find out the different parameters which are involved in this amplifier. Like, we can find out the voltage gain, that is the ratio by which the output voltage is increased with respect to the input voltage Vi or with respect to the source Vs. As well, we can find out the current gain, the ratio between the output and input currents. Also, we can find out the input impedance, output impedance, etc. But before that, we must draw the AC equivalent circuit for this amplifier, including the transistor model which we discussed earlier, that is RE model we will be discussing here, that is we will be taking the RE model for replacing the transistor. So, first of all, if we draw this AC equivalent circuit following the procedures which we discussed earlier, we can draw the AC equivalent circuit by first making the DC source as 0, that is short circuiting the DC source. Then we will be assuming short circuit part for the AC input as far as the capacitors are concerned, because the capacitors are chosen high values, so that under the signal which is being applied, the capacitors offer almost 0 impedance or capacitive reactance, such that it is like short circuit. Following these procedures, if we try to draw the AC equivalent circuit for this fixed bias transistor amplifier, we will make the VCC 0. Here it is only having the DC source VCC shared by this RB and RC. So, this source will have to be made 0 first, that is we will be grounding this VCC, and after grounding this VCC, we are left with the RB and RC resistances being grounded as per as this figure. Here RB and RC, these two resistances are connected to ground, and then we will be considering the capacitances C1 and C2 and make them short circuit because we are drawing the AC equivalent circuit, and as these capacitors are having large values, so it is almost equivalent to being short circuiting as far as AC is concerned. So, this part involving C1 and C2 will be short circuit as far as this signal is concerned. So, short circuiting means we will be simply removing this capacitances by short circuit part. So, as far as this base terminal is concerned, it will be having a RB which is grounded, as well as it will be connected to Vs, the signal at the input through this resistance Rs, and this coupling capacitor will also be now removed, and it will be a short circuit part from collector through this load resistance to ground, and another part will be there from the collector which is through this resistance RC to ground, because VCC is now grounded and emitter is already grounded. So, the whole circuit as per AC equivalent is concerned, it will be having these base collector emitter terminals as coming from the transistor. From the base terminal, this RB is connected to ground, and another part will be to this Vs through this Rs. So, collector will also be having this RC to ground, and RL is the load resistance connected at the collector to ground, it will be there. And now, as far as this transistor is considered, and we have already discussed how to draw this equivalent RE model, that is emitter resistance model for this transistor. So, we will be replacing simply the equivalent transistor model for the common emitter transistor. So, this base collector emitter, this is the transistor basically. So, you see here the base and emitter is having the resistance beta plus 1 RE, and collector is having a dependent current source beta times of IB, which is equal to IC. So, this part is replaced by this transistor model, and incorporating this transistor model into the whole circuit, we are getting this AC equivalent circuit for the amplifier. Now, we want to find out the voltage gain. For example, if we try to find out the voltage gain, we will be finding out the ratio between the output voltage and the input voltage. Now, we have to see which are the input terminals and output terminals. Always we will see from the source to find out the input terminals, and we will look from this load to consider the output terminals. That means the whole amplifier will be having the source and load external to it. So, as if we are sitting at the source and looking into the amplifier, in that way we will have to find out the parameters. Similarly, as far as the output is concerned, we will be looking from the load, as if we are sitting on the load and looking into the amplifier. So, this point is important because we will have to exclude the source and load while finding out the parameters in the whole amplifier. So, in between these two dashed lines is the whole amplifier, and the source and the load are external to it. So, now if we want to find out what is the voltage gain, that is the gain means the amplification between the output voltage and input voltage. So, the output voltage is between these 2 points, that is the voltage across this load resistance, and input voltage is between these 2 points. Vi is this input voltage and V naught is the output voltage, and conventionally this input and output currents, if we consider, they are into the amplifier. Customarily it is shown as direction as into the amplifier. So, I, that is the input current which is coming from the source, it will be flowing into the amplifier at this input terminal. So, this is the input current, and output current at this output terminals into the amplifier. So, the I naught current is flowing through this resistance RL into the amplifier, and input current is coming from the source into the amplifier. Now, if we look into this input current, we notice that the input current is having 2 parts. One part is through this resistance RB, and the other part of the current is through this resistance beta plus 1 RE. So, this input current basically has 2 parts, one is through this, one is through this. And the current source at the output, if we consider, IC is the current source which is equal to beta times of IB, and so the current which will be flowing, it will be flowing in this direction, it will be going to the output side. Input current, base current will be coming and it will be flowing like this. So, here the beta times of IB current, which is the collector current, has actually 3 parts. One is through this RC, one is through this R naught. R naught is the output resistance of the transistor. So, this very conveniently we generally ignore because it is having a very high value in the order of megohms, but to be exact this should be there, and afterwards we can ignore it. If we are told that it is very large, you can ignore it, but for the time being, while drawing the exact circuit, equivalent circuit, we will be having this R naught at the output side. This R naught is that output resistance of the transistor, common emitter transistor, and that is generally having very high value. So, this current, collector current beta times of IB has three parts. One is through this RC, one is through this R naught, and the other is through this RL, which is nothing but the conventional output current I naught as it is shown here. Now, if we want to find out input impedance, Zi is denoting the input impedance, we have to take the input terminals, find out the voltage at this input terminals is Vi divided by the current II, input voltage by input current will be the input impedance. And output impedance, we will be looking into the output terminals from the load and we will be finding out what is the output impedance by taking the ratio between V naught and I naught, that is V naught by I naught, making the input source 0, that is Vs you make 0, that will make Vi 0, means IB will be 0, so IC will be 0. So, we will be left with these two resistances being in parallel at the output side. So, that will be constituting the output resistance. So, these parameters we are going to find out, but first of all, one thing is to notice that while finding out these parameters, we will be excluding this source and load from this amplifier. That means, we will be looking from the source to the input side, or we will be looking from the load to the output side while finding out these parameters. So, one by one we will be finding out these parameters from this equivalent circuit. So, if we want to find out what is the input impedance Zi. So, input impedance means the ratio between Vi and II. So, Zi is equal to Vi by II. Now, we can find out what is Vi, input voltage. If we look into this figure, input voltage between these two terminals or 2 points, the voltage across this resistance beta plus 1 Re or the voltage across Rb, that is the input voltage. So, we can find out in two ways, that is the current which is flowing through Rb multiplied by Rb, that is the Vi, or current Ib multiplied by this resistance beta plus 1 Re, that is the input voltage. So, we will be following the latter, that is we will be following the input voltage expression, that is Ib into beta plus 1 into Re, and the denominator is II. Now, our purpose is to eliminate those active components, like we will be eliminating or cancelling out the currents and we will be left with only the passive elements. So, that is why this IB, if we want to express again in terms of II in order to cancel them out, if we look back into the circuit and find out what is the base current. So, base current is that part of the current which is flowing through this resistance coming from II. Input current is II, one part goes through this resistance Rb and the other part is through this resistance beta plus 1 Re. So, now we are interested in finding out Ib. So, what is Ib? Ib is equal to these two parallel paths are there. So, current division is taking place. So, II into Rb divided by Rb plus beta plus 1 Re, that gives us the value of Ib. So, expressing that Ib in that way, Ib is equal to II into Rb by Rb plus beta plus 1 into Re, and the remaining terms are there beta plus 1 into Re divided by II. Now, we can very well cancel II and II. So, we are left with Rb into beta plus 1 Re divided by Rb plus beta plus 1 Re. So, this is the exact expression for the input impedance for this amplifier in the fixed bias mode, and here we find that all these parameters are passive parameters, means they are either resistance or they are either their current gain beta, and this Re, in fact, we will have to find out this small r small e, that is the resistance coming from the transistor model, and we can find it out in this particular example. It will, if we want to find Re, we can find out because Re is nothing but 26 millivolt divided by emitter current, capital I capital E. Now, once we know IE from the DC equivalent circuit, we can plug in the value here and find out this small r small e. That exercise has to be done in order to proceed further. So, in fact, in order to find out all these parameters, we have to consider both the DC equivalent circuit and AC equivalent circuit. DC equivalent circuit we have to consider because we want to find out what is small re. So, after we find out small re, we can plug in here and we can find out the other parameters. So, input impedance we have found out, and here Zi can be expressed as a parallel combination between the two resistances Rb and beta plus 1 Re. That is exactly what is happening, because if we look into this expression RB into beta plus 1 RE by RB plus beta plus 1. It is nothing but the parallel combination of these two resistances RB and beta plus 1 RE. And in fact, this is very obvious. If we look into the circuit from the input terminals, then there are two resistances at the input, one is RB and one is beta plus 1 RE, both are in parallel. So, intuitively also we can see that this is the equivalent parallel resistance between these two resistances which are in parallel. So, that is what exactly we are finding out here, the parallel impedance between these two resistances, that is RB parallel beta plus 1 RE. So, this is the input impedance. Now, if we look into the output circuit and find out what is the output impedance, here we have to find out looking from this load. So, output impedance can be found out if we make this input voltage 0, because we are interested only that quantities in the output side. So, input side components or input side currents or voltages must not interfere with this output side. That is why if we make this Vi 0, then IB will be 0, so IC will be 0. So, this is like open circuit, this part will not be there. So, only we will be left with two parallel resistances RC and R naught, because our circuit will be like this part will be IB is 0, so IC is equal to 0, and there are these two resistances, one is RC and one is R naught, small r naught, that will be there at the output side, and we are finding out this output impedance. So, this output impedance is the parallel impedance RC and R naught. So, output impedance is RC parallel R naught, making thus input Vi is equal to 0. That is the procedure to be followed in order to find out what is output impedance. Now, at this point I want to mention that if R naught is considered to be very large, which is actually the case, its order is in the order of mag ohm 10 to the power 6. So, as compared to RC, it is higher. So, we can neglect this resistance or we can ignore this resistance because it is very high. It is almost like infinity. If it is very high or infinite, what happens is that there will practically be no current in this part, because infinite impedance it is offering. So, it will not be, current will not follow this part. That means, it is like open circuit, R naught will be simply ignored. Then we are left with only RC. So, then we can say that RC is the output resistance. This is the case when you ignore R naught. R naught means the output resistance of the transistor. So, these two parameters Zi and Z0 we have found out. Now, what about the voltage gain? The voltage gain is the ratio between the output voltage and input voltage. That means, it is a ratio between V0 and Vi. V0 and Vi, if we look back, what is V0 here? This V0 is nothing but I0 into RL, but with a minus sign, because we have denoted V0 as upper point is positive with respect to the ground, but this I0 is following in this direction. This is I0. So, I0 is this current. So, it is flowing from a higher potential to lower potential as far as this sign is concerned. So, the voltage drop, if we consider it as V0, it will be I0 into RL with a minus sign. So, minus I0 RL will be equal to V0, because as far as direction of current, this is positive point, this is negative point, but voltage we have denoted as V0 as upper point is positive. So, V0 is equal to minus I0 into RL, and input voltage we know that we have already found our input voltage IB into beta plus 1 RE. So, replacing these values here, V0 is equal to minus I0 into RL and Vi is equal to IB into beta plus 1 RE. Now, again if we replace what is the I0, now if we look back into the circuit, what is I0? I0 is that part of current of IC which is flowing through this resistance RL, because if we look into this output side, the current source is beta times IB, which is equal to IC. This current is flowing in this output side, and this current has three parts. As I have just now mentioned, it is one part of the current beta times IB is flowing through RC, other part is through R0, other part is through RL, and we are interested in finding out that part I0. So, if we combine these two RC and R0 together as RC parallel R0, that is one resistance, say, other is RL. Now, according to current division, beta terms of IB is divided into this parallel resistance and this resistance. So, we are interested in finding out this current through this resistance RL. So, that will be equal to beta times IB into this equivalent parallel combination RC parallel RL divided by RC parallel RL plus RL, capital RC parallel R0 plus RL. So, that is here written beta times of IB minus sign is there because minus I naught RL is the voltage at the output. Here we are replacing this I naught by beta times IB into RC parallel R naught by RC parallel R naught plus RL into RL. RL is already there in the original expression, and VI input voltage is given by IB into beta plus 1 into RE. So, now we can further simplify this expression by writing minus beta into IB cancel. So, upper term or the numerator term, if we again consider, it is nothing but parallel combination between these three resistances RC, small r naught and capital R, capital L, because this is RC parallel R naught into RL divided by RC parallel R naught plus RL. This is the parallel combination between this and this. So, finally, we have a parallel combination between all these three in the numerator divided by beta plus 1 into RE. Now, as beta and beta plus 1 are almost equal because beta is a high value, suppose 100 and 101, there is not much difference, it is almost equal. So, we can very conveniently cancel them out. Then it gives a further simplified expression, and that is equal to minus RC parallel R naught parallel RL by RE. And here again, if we now consider that R naught is very high, then we can further ignore R naught, and finally we get an expression. If R naught is ignored, then we will be further getting another further simplified expression of AV, which is equal to minus RC parallel R naught RL divided by small RE. This is a very simple expression to even remember, because now we have ignored R naught because it is very high, but this is the exact expression, and further simplifications can be done conveniently looking into the practical aspects. Now, one thing to be noted is here the minus sign. Actually, this minus sign has a significance or it has a meaning, because minus sign means the phase reversal of 180 degree, or the output voltage is out of phase by 180 degree with the input. So, that is actually denoted by this minus sign. 180 degree phase shift occurs between the input and output signals, that is why V naught by Vi is having a minus. So, if I have input voltage like this, I will be getting an output voltage which will be amplified no doubt, but it is out of phase by 180 degree like this. So, we will be getting a 180 degree phase difference between the input and output, and that is denoted by this minus sign. Now, if we want to find out another term which is current gain. Current gain is the ratio between the output current I naught and input current II. Now, output current, as we have just now done, can be expressed as beta times of IB into RC parallel RL by RC parallel RL plus RL divided by II. Again, this IB can be further written as beta, if I consider IB from the equivalent circuit, it is better to look into the equivalent circuit to find out what is IB, II into RB by RB plus beta plus 1 into RE, that also we have done earlier. So, just writing in that way, that is what is done here, II into RB by RB plus beta plus 1 into RE, that is the value of IB, and the rest of the part is as it is divided by II. So, now I can cancel out this II and II. So, now we are left with II is equal to beta times of RB by RB plus beta plus 1 RE into RC parallel R naught by RC parallel R naught plus RL. So, mind it, here we cannot make a parallel combination because the numerator does not have this RL term. So, as it is we have to write, only further simplifications can be done only if we consider that here in this term we can look into that beta plus 1 RE, RE is small. So, if we write down that RB plus beta plus 1 RE equivalently or approximately, then only we can do further simplification, but let us not do and keep it in exactly in the same way. Now, of course, one thing we can do is R naught is ignored. If R naught is ignored, then we will be left with beta into RB by RB plus beta plus 1 RE into RC by RC plus RL. That much simplification we can do. And here one thing to be noticed is that there is no phase shift between the output and input currents. If output current is towards the transistor, input current will also be towards the transistor. There is no sign change, so there is no phase reversal. So, the current gain does not have any phase shift, only the voltage has. But one more thing I would like to find out here is the voltage gain with respect to the source. If we look into the voltage gain, what we have just now found out, it is V naught by Vi. That means, with respect to the input voltage, we are finding out the ratio by which the output voltage is increased. The input voltage means this voltage. But again, if we look into what is Vi with respect to Vs, because one part of this input signal which you are giving as input, a part is lost in the resistance Rs, because there is a drop in the resistance Rs, and the rest is what is available as Vi. So, if we want to find out the voltage gain with respect to the source and term it as AVS, denoting the voltage gain with respect to the source, then we have to write it V naught by Vs, and that can be further expressed by chain, which is V naught into Vi into Vi by Vs. Because V naught by Vi we have already found out, we can write it as AV, but what about Vi by Vs? Because we have seen that the signal Vs which you are applying at the input, there is a resistance at which there is a drop, rest part is available as Vi. So, this voltage we want to express it in terms of Vs. So, what will we do that voltage? Because this input side is having a input impedance Zi, which we have already found out. So, we can find out voltage division, because voltage division is taking place here. So, what is Vi? Vs into Zi by Zi plus Rs. This is the voltage available at input. That is what is written here, Vs into Zi by Zi plus Rs, and Zi we have found out, that is equal to that Rb parallel beta plus 1 Re, that is Zi, that we have just now found out, that is Rb parallel beta plus 1 Re. So, putting the value of Zi, we can find out now the expression for Vi by Vs, that is equal to Zi by Zi plus Rs. So, what is AVS? Is equal to AV, this part is AV into Vi by Vs is nothing but Zi by Zi plus Rs. So, this is the voltage gain with respect to the source. We are finding out two things, one is with respect to the input voltage, one is with respect to the source. So, this was about the fixed bias configuration. Now, let us go to another configuration which is having a resistance at the emitter, that is self bias is there, but with a bypass capacitor. If we consider this figure, this is an self bias in the emitter is there, that is the difference between the fixed bias and this bias, which is called the emitter bias configuration, but there is a bypass capacitor. Now, if we look into this circuit and compare with the earlier one, there is no difference as far as the AC equivalent is concerned, because as there is a bypass capacitor and it is like short circuit in AC. So, the emitter resistance R will be bypassed by the current, emitter current. So, it is nothing but the same circuit which we just now analyzed, because the equivalent will be like this only. Because the emitter is bypassed, it will be directed to the ground, not by this, not through this resistance in the emitter Re, but it will be having a short circuit path, and the others are exactly same. So, this circuit and the earlier fixed bias circuit does not have any difference as far as AC equivalent is concerned. So, we need not analyze it again, and similar analysis as the earlier are still holding for this circuit, that is this amplifier with self bias in the emitter with a bypass capacitor. But if the bypass capacitor is not present in the emitter, then of course, the circuit will be different, and that is what we are going to do. That is common emitter bias configuration without the emitter bypass capacitor. If we consider, bypass capacitor is not there, mind it, and that is why there is the existence of this Re, that is the emitter resistance in the emitter part. So, if we want to draw the equivalent circuit for this amplifier following the usual procedure that we have followed earlier, we will be getting a circuit like this following all the necessary procedure. It will be having this is the transistor side, equivalent model for the transistor for a common emitter, and the input is having this Rb as well as the source and resistance Rs, which is the series resistance with the source, and the output is RL, the load resistance, Rc, Re is there. But here one thing is missing is that R naught we are ignoring, and R naught is conveniently ignored here because inclusion of this R naught will further complicate the whole analysis. So, for very conveniently we can ignore R naught, that is what is done here, R naught is ignored. Otherwise, it will be very complex circuit to analysis, and in order to avoid all those complications, we can very well ignore R naught, as it is practically also true. So, excluding that R naught, we are having this circuit at the output side only RC will be there, RL of course is there, which is the load resistance, and RE is there, which is in the emitter. The current flowing through this emitter resistance RE, if we look, it is the emitter current IE, that is equal to beta plus 1 into IB. So, this resistance RE can be very well written as the reflected resistance beta plus 1 RE. Instead of RE, we can write beta plus 1 RE in the emitter resistance, and we can keep this IB same, that is same current IB is flowing, having a resistance here beta plus 1 RE. That is conveniently done, because then our analysis will also be easier and we are not doing anything wrong, because the voltage drop, if we consider, the voltage drop is IB into beta plus 1 RE plus IE into RE, but I is again nothing but beta plus 1 IB. So, the voltage drop is same, only thing we are writing it differently, that is instead of RE we can write beta plus 1 RE, and the current IB is same, other current is beta times IB. Of course, this should be having a symbol of a diamond, because this is the symbol for the dependent current source, it is not a circle, circle is independent current source. So, this is wrong. In order to write it correctly, we should have a diagonal signal, which is the symbol for a dependent current source, because it is a dependent current source, dependent on IC is dependent on IB. So, now in this circuit, all the parameters which we have just now found out for the other circuit are to be found out. So, for that, starting with input impedance. Now, input impedance, if I consider Vi by Ii is the input impedance, looking from this source into the input, that is the input impedance. Now, input impedance is basically parallel impedance between RB and this whole resistance. Now, this whole resistance is this resistance plus this resistance, let us name it as ZB for clear understanding. I am denoting it separately, ZB is equal to Vi by IB, that is this voltage by the current IB. So, as just now we have expressed it as beta plus 1 into RE, keeping the IB same. So, what is this resistance? This resistance is nothing but the series resistance between beta plus 1 RE and beta plus 1 capital RE. So, that is how we are writing here Vi is equal to, as the input voltage is IB into beta plus 1 into RE plus beta plus 1 IB into RE, we are writing it in a different fashion, that is we are keeping IB is equal to same and writing it beta plus 1 into RE plus RE, where now we can denote ZB is equal to beta plus 1 RE plus RE, that is the whole resistance from this point to this point, beta plus 1 into small RE plus capital RE, that is denoted by ZB. So, now we can find out the input impedance easily. So, what is this input impedance? This resistance RB parallel to ZB, Zi is equal to RB parallel ZB. So, that is input impedance Vi by Ii. If we write down the whole expression of Vi, IB into ZB is this Vi divided by Ii. Again, if I proceed in that way which we used earlier, IB is equal to Ii into RB by RB plus ZB, that is this current flowing through this resistances is IB. Find out that current is equal to Ii into RB plus Ii divided by RB, Ii into RB by RB plus this whole resistance, that is current division. So, that is what is written here, Ii into RB by RB plus ZB into ZB by Ii, cancelling out these two. So, I am left with RB into ZB by RB plus ZB, which is RB parallel ZB. So, we are getting, even if I look into the circuit from this terminal, find out Zi, this is intuitively I can say RB parallel this whole resistance, and that is what I have also found out proceeding from this initial expression for Zi, that is giving the same result. So, this is input impedance. What is output impedance? If we look into the output circuit, I look into the amplifier from the output side, that is from the load. We have to look from the load, that is output impedance. Skipping this Vi 0, making Vi 0 means this IB is also 0, that is it is like this part is open. So, if this part is open, that means I am having only one resistance RC at the output. So, output impedance is Z naught is RC. Now, voltage gain, if we want to find out voltage gain AV following the expression V naught by Vi, doing all these replacements, like V naught is what? V naught is minus I naught into RL, like previous example. This is the direction from bottom to top of this current. So, minus I naught into RL is equal to V naught divided by Vi. Vi is again IB into this whole resistance ZB. So, that is followed here, minus I naught into RL by IB into ZB. Now, again what is I naught? That part of the current which flows through RL. So, the current which flows through RL is I naught. Now, the dependent current source beta IB, that is what is flowing in this output circuit, because you see the current part, one is IB base current, one is the collector current, both are combined here to give the emitter current. Again, as the current which is starting from a source, it should end up at that same source. So, the current after this point will be again IB will be flowing this way and IC will be flowing this way. So, IC has again two components, one is through RC, another through RL. I am interested in finding out the current through RL, that is what is I naught. So, beta times of IB into RC by RC plus RL is I naught. That is what is done here. It is beta times of IB into RC by RC plus RL into RL. Since R naught is not there, there are not 3 parts, there are only 2 parts. So, that is what is the difference here, it is made, otherwise it will be more complex, divided by IB into ZB equal to minus beta into IB cancel RC RL by RC plus RL. Again, this is nothing but the parallel combination between the RC and RL. In the denominator ZB is there. So, what is the voltage gain AB? That is equal to minus beta into RC parallel RL by ZB. Again, ZB we can replace, that is equal to beta plus 1 into small r e plus capital R e. So, this is the expression for voltage gain V naught by Vi. Now, if we want to find out the voltage gain with respect to the source V naught by Vs, that is AVs, if we want to find out what is B naught by Vs, as we know V naught by Vs is equal to AV into Zi by Zi plus Rs. So, Zi we know, we have found out Zi, simply replacing by this quantity for Zi, we can now get what is this AVs, because AV is this AV what we have just now found out. So, voltage gain we have found out. Now, if we want to find out the current gain, I naught by I naught by II is the current gain, and I naught again we will be writing in the same way, beta times of IB into RC by RC plus RL, that is the part of the current which flows through RL, and divided by II. Again, if I replace IB by that part of the current which flows through the ZB, that is the IB, out of the input current II, this portion goes through this ZB, II into RB by RB plus ZB is IB, and the rest is this one same RC by RC plus RL divided by II. So, then this is those two cancel. So, current gain becomes beta into RB into RC by RB plus ZB into RC plus RL. So, this is the exact expression for current gain. Of course, R naught is ignored here. So, this circuit, that is the circuit having the emitter bias, emitter resistance, which is unbypassed, there is no bypassing capacitor, then we get these expressions or parameters which are involved in the amplifier. Now, another example which is very popular, which we have earlier discussed and which is very much used in all these practical amplifiers, is the voltage divider bias configuration. So, if we now have this common emitter voltage divider bias configuration, this is the circuit having R1 and R2 parallel at the terminal B and connected to VCC. I mean, these resistances R1 and R2 are now two separate resistances instead of one single resistance RB, as was discussed in the earlier cases. Others are same, others and the other parameters in this circuit are same. So, in fact, if I analyze this circuit, draw the AC equivalent circuit, it will be similar, only difference will be there, that is we have to find out the Thevenin's resistance RB, which is the parallel equivalent of R1 and R2, and that will be the factor which will be differing than the earlier circuits. So, if we draw the AC equivalent circuit for this voltage divider biasing scheme, following the usual procedures, we have R1 and R2 being parallel, that AC equivalent circuit will be having R1 and R2 parallel because it is grounded, since VCC is grounded now in AC equivalent circuit. These two resistances which are both connected at base and connected to ground, this also will be grounded because this will be grounded, this is also grounded. So, these two are parallel. So, this parallel equivalent, if I denote it by capital R capital B, which is R1 parallel R2, all others are same, and then the earlier discussed circuits, RC, R0 is kept, RL is there. So, now in this circuit we can easily find out what are the parameters involved, like we can find out what is the input impedance. Input impedance, if I look from this point, find out what is input impedance Zi, that is this resistance parallel to this resistance, RB parallel beta plus 1 RE, and this RB of course is R1 parallel R2, that is the only thing which is different than the fixed bias circuit. And as this emitter is bypassed by this capacitor, so ultimately we are having the short circuited path like this. So, what is Zi? Zi is equal to RB parallel beta plus 1 RE. Even if you follow by this usual procedure of finding out Vi, dividing it by II, which will give you Zi, that will be giving you finally the same result. But I can intuitively very well see that this is nothing but the parallel combination between these two resistances at the input. I can immediately write down this input impedance like this. And similarly, if I find out the output impedance, I look from this load into the amplifier in the output circuit, look from here, look from this load, then it is parallel combination between RC and R0, that is the output impedance. So, these two can be immediately found out. Now, again if I want to find out in the traditional way of finding out all those expressions of voltage and current etc., then also you will be left finally we will be getting the same result. If I find out Zi is equal to Vi by II, again what is Vi? Vi is Ib into beta plus 1 RE divided by II. What is Ib again? I replace in terms of II that part of the current which flows through the resistance beta plus 1 RE, that is Ib. So, II into Rb by Rb plus beta plus 1 RE, that is this current Ib into beta plus 1 RE divided by II. So, now these two cancel. So, I am left with Rb into beta plus 1 RE by Rb plus beta plus 1 RE. This is nothing but a parallel combination between these two resistances Rb and beta plus 1 RE. So, again Rb is, we know that this is R1 parallel R2. So, as per as expression wise, if I look back and see the earlier circuit, there is no difference, because earlier also in fixed bias scheme we have found out that input impedance Zi was Rb parallel beta plus 1 RE, and this is also Rb parallel beta plus 1 RE. Only difference is that now we are having Rb as parallel combination between R1 and R2, not a single fixed resistance, that is the difference, others are same. And now output impedance, as we have seen RC parallel R0, I need not again analyze in details, that is very clear. And voltage gain, AV can be found out in a classical way of finding out from this voltage and finding out the gain. So, V0 is equal to I0 minus I0 into RL. Here this is V0, current is flowing in this direction. So, minus I0 into RL is V0, as V0 has been denoted, upper point is positive with respect to the ground. And again Vi we know Ib into beta plus 1 RE. So, that is replaced here, and again finding out what is I0 from the output circuit, the current source, that is beta Ib, that is this current is divided into 3 parts. I am interested in finding out this current through RL, that is equal to beta Ib into RC parallel R0 by RC parallel R0 plus RL, that is the current I0. This RL is already there, divided by Ib into beta plus 1 RE, and now I can cancel out this beta and this Ib and this Ib, and I am left with minus beta into RC parallel R0 into RL by RC parallel R0 plus RL. This is nothing but the parallel combination of RC parallel R0 and RL. So, finally, I am getting parallel combination between these 3 resistances RC, small R0 and capital RL. That is what is here, minus beta into RC parallel R0 parallel RL, and in the denominator beta plus 1 into small RE. So, this is the exact expression that we obtain for this voltage divider biasing scheme, and here we can conveniently further simplify by approximating that this beta plus 1 and beta, as these are almost equal, we can cancel out these 2 and then write down this expression as minus RC parallel R0 parallel capital RL divided by RE. So, this is a further approximation than this. Again, even further approximation I can do by conveniently ignoring R0, because in all practical cases R naught is very high. So, I can even further approximate by writing it down as minus RC into RL, minus RC parallel RL by RE. So, this is after approximation one step further. So, finally, we can see that this voltage gain is actually high in common emitter amplifier, because R is small, its order is in the order of ohms. So, this is less as compared to the parallel combination of RC and RL, because RC RL are generally it is in the order of kilo ohms. So, finally, in the numerator if I get a kilo ohm order of quantity and in the denominator is a ohm order of, so 10 to the power 3, I mean it is almost like 100 times or I mean more than that, you get an enhancement of the input signal. That is actually that what happens in common emitter amplifier. And now if I again try to find out what is the overall voltage gain with respect to the source, how much voltage gain I am getting. If I apply a source which is in the order of 1 millivolt peak to peak, suppose I am applying a small signal Vs, its peak to peak value is a 1 millivolt, then how much amplified signal at the output I am getting, that measure can be done, that can be found out by finding the overall voltage gain AVS, because AVS is nothing but V naught by Vs, final output voltage by input signal at the source, that is actually giving you the measure of overall voltage gain. And by using the expression that we have already discussed, AVS is nothing but AV, the voltage gain, into Zi by Zi plus Rs, then we can find out what is this overall voltage gain. And if we do this, we will be finding out that the voltage gain with this keeping with respect to the source, if this voltage gain, overall voltage gain a bit less than the voltage gain AV, because if you look into the denominator Zi plus Rs, Rs is a series resistance, it has a value, small value it may be, but it still has the denominator value being higher than the numerator in this case. So, it will be a fraction. So, AV multiplied by a fraction means ultimately it will be a reduced value than AV. So, overall voltage gain, if we consider having a series resistance in the source, it will be lesser than AVS is generally lesser than AV. So, overall voltage gain is lesser than the voltage gain which would have been possible had there been no series resistance with the source. And similarly, current gain we can find out AI. So, AI current gain I naught by II, and I naught is the current which flows through the load resistance RL. So, the load resistance RL is having that current I naught which is a part of the current beta times IB, and that current is beta times IB into RC parallel R naught divided by RC parallel R naught plus RL. So, that is replaced here RC parallel R naught by RC parallel R naught plus RL. So, that is the part of this current beta times IB which flows through RL, which is I naught divided by II. Now, again we can express this IB as II into RB by RB plus beta plus 1 RE, because that is the part of the current which is flowing through this beta plus 1 RE, that is the base current. So, out of the input current II, a part is flowing through this beta plus 1 RE, that is the base current, that is what we are finding or replacing it with. So, that is nothing but II into RB by RB plus beta plus 1 RE. So, that is here we are replacing, instead of IB I am writing it II into RB by RB plus beta plus 1 RE, others are same, this is same as it is. Then I can now cancel out, writing it in that order has a purpose of cancelling out those two IIs. So, now we are having current gain expression as beta into RB by RB plus beta plus 1 RE into RC parallel R naught by RC parallel R naught plus RL. This is the exact expression of current gain in voltage divider biasing scheme. There is no phase difference in the current gain, that means there is no phase shift between the input current and output current, and in the voltage gain there is a phase reversal of 180 degree, that is the input signal is out of phase by 180 degree with the output signal, and the current gain, if we look into the current gain, I can further simplify it by ignoring R naught. If I ignore R naught, that will be RC by RC plus RL, and beta is generally very high in common emitter, it is 100, even more than 100, it can be up to 500 say. So, even if it is say in hundreds, beta is in hundreds, we will be getting the voltage gain very much higher, and that is the basically that is the reason why common emitter amplifiers are used for voltage amplification. You get a high voltage gain, and the high voltage gain actually can be seen to be here, because small r is in the denominator, that is very small as compared to the numerator. So, it is always greater than 1. In the order of hundreds also you get voltage gain in common emitter amplifier. So, for a voltage amplification purpose you use common emitter amplifier. Of course, there is a phase reversal of 180 degree, and that has to be remembered. So, now in this discussion we have now today covered the different biasing schemes, and if we understand the way to proceed in the AC equivalent circuit to find out all those parameters which are involved in the amplifier, like voltage gain, current gain, and input impedance, output impedance, these are the major parameters, and a related parameter may be power gain, that you can find out. If I multiply voltage gain and current gain, we will be getting the power gain expression also, but that is just a secondary gain. I mean I get from voltage and current gain. So, once I know voltage and current gain, I can find out the power gain. So, the major parameters we have found out, that is we have found out the input impedance and output impedance, we have found out voltage gain and current gain for different biasing schemes. Out of all these biasing schemes, the voltage divider biasing scheme which we have just now discussed is very popular, because it generally has the capacity to stabilize the operating point. So, actually although we have discussed today the amplifier from the perspective of the AC equivalent circuit, but prior to it we have already discussed the biasing scheme. So, once we have set upon a good biasing scheme stabilizing the Q point or the operating point, which should not shift afterwards, even because of change of beta, because of change of the transistor, or because of temperature change, there should not be significant change in the or shifting of the operating point. After ensuring the biasing only, we proceed to find out the amplification of the amplifier that we are considering. So, as voltage divider biasing scheme is very popular, because it guarantees the stability of the operating point. So, that is why it is very much used in practice. So, with the voltage divider biasing scheme, along with those capacitances which are coupling capacitances as bypass capacitance, we have found out all these parameters which are involved in the amplifier. So, we can find out for any biasing scheme if we proceed in a similar way from the starting principle, that is, in order to find out the voltage gain, we must proceed from the starting point, which is nothing but the ratio between the output voltage and input voltage. So, then what is output voltage, what is input voltage, those expressions we have to find out, keeping in mind the AC equivalent circuit or referring to the AC equivalent circuit along with the transistor model being incorporated into it. So, we can find out any parameter for any biasing scheme amplifier proceeding in the same manner which we discussed today, and even if some of the resistances may be absent. For example, if we have no resistance in the emitter, that is emitter is having say no resistance in this circuit, if there is no resistance in this emitter or simply it is connected to ground, then also we can find out. There is no difficulty in finding out the parameters for any circuit with even the resistances being, some of the resistance being not there, instead of 2 there is only one single resistance, as we discussed in the first case, just by proceeding from the first principle. So, always we have to proceed with the first principle. That means, if we want to find out the input impedance, it will be Vi by Ii. But one thing to be noted here is that we will be considering the source and the load outside the purview of this two terminal network. That means, input side will be having the source resistance input terminals will be having the source resistance and source outside, and the output terminal will be having the load resistance outside. So, this point has to be remembered, and the whole network will be in between these 2 points or 2 pair of terminals, input and output, 1 1 dash and 2 2 dash if we name it. So, now in that way we can proceed and find out the parameters which are required or which are important for this amplifier, and we can find out for any of the configurations. So, basically if we are asked to find out what is the voltage gain of this particular amplifier, then by plugging in all the values we can find out the gain. So, we will be also considering next the numerical example. If I want to find out numerically the value of any of the parameters for any of the configuration, we can do that. So, today's discussion actually leads us to going a step further for exactly finding out the amplifier parameters, but still we have to keep in mind that we are still considering the small signal analysis. That is, our signal is small enough to still make the transistor operate in active region only. If the transistor should not be overdriven into either saturation or transistor being overdriven into cutoff, these two conditions should never arise, then only this whole discussion is valid. That is, whatever small signal analysis we are doing, we are doing the small signal analysis and applying it to the transistor amplifier, and in view of this small signal being applied, we are still in the active region, or the transistor is operating in the active region. That is why we can write down that IC is equal to beta times IB. So, if it is saturation, we are never able to analyze it in the way that we are analyzing. So, this point has to be kept in mind, that we are dealing with a small signal analysis and we are trying to find out all those parameters involved in the amplifier, taking example different biasing schemes and finding out all this. So, today we have discussed about common emitter transistor amplifier, BJT common emitter configuration with different biasing schemes. Also, there are common base and common collector amplifiers, and these common base and common emitter amplifiers are basically used for some typical special applications like a voltage buffer or current buffer, etc. it will be used. So, we will be discussing that, but then today we have discussed about the most frequently or commonly used amplifier for voltage amplification, suppose, and that in that case generally the common emitter amplifier is used. So, we have discussed extensively about common emitter amplifier in different configuration of biasing, but we will also discuss about common base and common collector amplifiers next.